In this video, we will discuss Unit 1, that is Introduction to Optimization Algorithms. Topics covered in this video. First, we will start with what is optimization, optimization aim, optimization key components, optimization problem statement, and then we have different optimization problems: constrained, unconstrained, and multi-model optimization problem. And we will try to understand one optimization problem, that is transportation problem, using numerical example. So first question is, what is optimization? As we know, optimization is fundamental concept in various fields including engineering, mathematics, computer science, economics, finance, medical field, and other. Optimization is the process of finding best solution or a set of solutions from a range of possible options. And optimization aim is to either minimize or maximize the objective function. Now, what is objective function? Objective function is a mathematical expression that represents the quantity that need to be optimized. For example, in a minimization problem, we want to minimize the cost. In maximization problems, we have to maximize the profit or to achieve high performance. For example, in this classical optimization problem, our aim is to minimize total transportation cost. So objective function is used to represent the quantity that need to be optimized. Next, you can see here we have two types of optimization problems: minimization problems and maximization problems. In minimization problems, aim is to find out minimum value of any objective function. For example, either minimize error, minimize cost, or minimize energy consumption. In maximization problems, aim is to find out maximum value of an objective function, either maximize profit, efficiency, or revenue. Next, we have optimization key components. First, decision variable, that is also known as design variables. Next, objective function. Next, we have constraints, feasible solution space, optimal solution. Last one, local and global optima, that we will discuss one by one in upcoming slides. Next, we have optimization problem statement. In optimization, our aim is to find out best solution from feasible set of solutions. Now suppose this is the best solution. The best solution is typically defined based on certain objectives. Now we will structure the statement of optimization problem. First, we will define objective function that need to be either minimize or maximize. This objective function is a mathematical expression that represents the quantity that need to be optimized, and we can represent objective function using f of x, where x is the vector of decision variables. So for minimization problem, we can denote it as minimize fx. For maximization problems, maximize f of x. Next, we have decision variables, that is also known as design variables. So next, we will specify the decision variables. Decision variables determine the solutions, and these are the parameters that can be adjusted to achieve the optimal solution, and we can denote decision variables as x is equal to x1, x2 up to xn. Next, we have constraints. Now we will introduce any constraint that solution must satisfy. Constraints are the condition, or you can say limitations, that restrict the feasible set of solutions. Here you can see we have two types of constraints: equality constraint and inequality constraint. In transportation problem, we will use both equality and inequality constraints. Next, we have feasible set. So define feasible set, that is set of all solutions that satisfy the constraints, and find out the best solution within the feasible solution space. So we can structure optimization problem: minimize objective function which subject to different inequality and equality constraints. Overall goal is to find out the values for the decision variables that either minimize or maximize the objective function and also satisfy given constraints. Optimization problem can have local and global optima. Local optima is the best solution within a specific range of feasible solution space, while global optima is the best solution across entire feasible solution space. Next, we have constrained optimization. Constrained optimization problems involve additional conditions that must be satisfied. Constrained optimization, our aim is to find out minimum or maximum value for any objective function that's subject to certain constraints on decision variables. Now we have different key components in constrained optimization: objective function, decision variables, constraints, and it also involves constraint. It can be both equality and inequality constraints, feasible solution space, and we need the optimal solution. Next, we have constrained optimization methods, analytical methods, numerical methods, and heuristic methods. In analytical methods, we have Lagrange multipliers. This method introduces additional decision variables, or we can say Lagrange multipliers, to convert constrained optimization problems into unconstrained optimization problem, and solution involve finding the critical points of the new function. In numerical methods, we have interior point method, penalty function method, sequential quadratic programming. Penalty function methods transform constrained optimization problems into a series of unconstrained optimization problems, adding penalty to the objective function. And last one, we have heuristic methods that we will discuss in Unit 3. Next, we have different challenges in constrained optimization problems. First, we have feasibility. Second, optimality and local minima. Then we have computational complexity. First, we have feasibility challenge. Find out the best solution that satisfy all constraints can be challenging for complex systems. About computational complexity, so depending on the nature of objective function, so some numerical methods can be computationally expensive. And about local minima, sometimes the algorithm is unable to find out the global solution as it is stuck in the local minima. Now we will discuss one classical optimization problem, that is transportation problem. Transportation problem is a real-world application that come to light in supply chain management and distributed planning. So here we will try to solve this transportation problem, and the objective is to minimize the total transportation cost. In this optimization problem, the goal is to minimize the cost of transporting goods from multiple suppliers to multiple consumers, and we have to satisfy certain constraints. Now for simplicity, instead of multiple supplier and consumer, we have just 3 suppliers, S1, S2 and S3, 3 consumers, C1, C2 and C3, and the transportation cost per unit is in dollar from each supplier to each consumer. We will count this cost in dollar. So as we already discussed in optimization problem statement, the structure of optimization problem, we have design variables, objective function, constraints, then we have feasible solution and the optimal solution. Suppose we have decision variables xij, I that is supplier and j consumer. So xij, that is it represents the amount of goods shipped from supplier I to consumer j. So we will use this variable to represent the quantities of goods transported by the suppliers to consumers, and this should be greater than or equal to 0 for all supplier and consumers. Next, we will define the objective function. The objective is to minimize total transportation cost. We will minimize the total transportation cost, that is sum of the product of the quantity shipped, that is xij, and cost per unit to transport, that is Cij, from supplier to consumers. So this is the objective function. Next we can see here transportation cost per unit is calculated in dollars from each supplier to each consumer. So from first supplier to first consumer it is, so first pair you can see here S1 C1, supplier 1 and consumer C1, the cost is $4 and S1 C2 $6, S1 C3 $8, S2 C1 $3, S2 C2 $2 and so on. So now we will use this transportation cost in the objective function. So here you can see now we will calculate objective function using this. Here you can see this is the cost $4 into x11. Here xij we discussed, this is the product. Xij, that is the quantity shipped between supplier and the consumer, and this is the cost per unit. So here we have for the first, so here you can see for the first pair it is $4. So here we have 4x11, then we have the quantity that is supplied between this pair, then for the second, third, up to so on. You can see we have two constraints here, supply constraint and demand constraint. So first we have supply constraint, second we have demand constraint. So for supply constraint, total quantity supplied by each supplier must not exceed available supply, that is available supply, that is SI. So the overall should be less than or equal to this value for each, and for second supplier it is 50, for third supplier it is 20, so this value should not be exceed. For demand constraint, next we have demand constraint, so each consumer should receive its demand. So for this constraint, the total quantity demanded by the consumer must be satisfied and equal to demand, that is Dij. Here this is the equality constraint and here this is the inequality constraint. For the first consumer it is 25, for second 30, for third 45. So here you can see we have supply constraint and consumer constraint. Supplier supplies, you can see S1 can supply 30 goods, S2 can supply 50 goods and S3 can supply 30 goods. Now we have demand constraint, so consumer demanded only, so C1 need just 25 goods, C2 need 30 goods and C3 need, and third consumer need 45 goods. Now so we have the cost values. Now we have to find out the values for xij. We can solve linear programming problems using optimization algorithms or using any software to find out the values of xij that satisfy both constraint, and these values must satisfy both constraint, demand and supply constraint. Right now we are not using here any optimization algorithm method that we will discuss in another units. So here we have, so here we will consider this shipping plan and you also satisfy both supply and demand constraint. For example, you can see here we have first value 25, so between first supplier and first consumer 25 unit is shipped, and between S1 first supplier and second consumer 5 units shipped, and value 0 represents there is no shipment. And the next pair you can see S2 to C1 0, there is no shipment, S2 to C2 25, S2 to C3 25 and S3 to C1 C2 is 0, there is no shipment, S3 to C3 it is 20. And you can see we have constraint, supply constraint we have for S1, S2, S1 first supplier can ship only 30 items. Here you can see total is just 25 plus 5 30. Second supplier can ship 50, so here 25 plus 25 50, and third supplier can ship only 20. And we have demand constraint, first consumer demanded only 25 items, second demanded 30 items, and here just 45, and it is. So here you can see both constraints are satisfied and we obtain the value for xij. Now we will use these values here. Now we will use this value in this objective function and find out the total transportation cost. So put all the values here. First x11 it is 25, x12 5, x13 it is 0, x21 it is 0, x31, x22 25, x23 is 25, x31 0, next x32 is also 0, and x33 is 20, and we got the minimum transportation cost is 345. So we obtained this minimum transportation cost. So here we calculated total transportation cost 345. This value represents the total money that suppliers will spend on transporting goods to the consumers. So this is combined cost for all suppliers S1, S2 and S3. So now next question is how much each supplier will contribute to this total transportation cost. Now to determine how much each supplier will contribute, we will consider the individual transportation for each shipment from each supplier. For first supplier, we can see here we have just two shipments from S1 to C1 and S1 to C2. So here S1 to C1 it is 25 into 4, that is 100. Next we have S1 to C2, that is 5, so 6 into 5, that is 30. First supplier total contribution is here $130. Next for the second supplier, here we have two pairs, S1 to C2 25 into 2 50, S2 to C3 that is 25, and this is 125. So total contribution from second supplier is 175. For the third supplier we have S3 to C3, that is 20 into 2 40, so it will pay just $40. So when you will total all this, it is $345. Now you can see the contribution for each supplier. First will pay 130, second $130, second will contribute $175, and the third will contribute $40. The constrained optimization problem, or you can say it is also multivariable optimization problem. Now we have unconstrained optimization problem. Again the aim is to find out the minimum or maximum value for any objective function, but here we have no constraint on the decision variables. So goal is to find out the value of the decision variables, but right now we have no constraint, there is no condition like we have in constrained optimization problem. So we have just given a function and we have to find out minimum or maximum value, objective function, decision variables and optimal solution. There is no constraint. Now you can see different methods that we can use for unconstrained optimization: analytical, numerical and heuristic. In analytical we have calculus, then we have gradient, Newtons and other methods. And the challenges, again we have local optima, algorithm stuck in local optima, unable to find out the optimal solution, best solution, computational complexity. Next we have multimodal optimization. Multimodal optimization problems involve the process of finding multiple optimal solution in search space. So instead of finding just one optimal solution in the search space, in multimodal optimization problems the aim is to find out multiple optimal solution in the search space. So in many optimization problems there may be multiple optimal solution and all are equally good according to objective function. Such solution exist in the peaks, or you can say the modes of the objective function. So challenge is to locate all of them. Objective function landscape where the multiple optimal solution exist. Then we have modes. Each mode represent an optimal solution. Goal is to identify as many as possible. And here we have different multimodal methods. We can use evolutionary algorithms, genetic algorithm, PSO, or we can use swarm algorithm, and other methods are given here, hybrid technique and all. that are covered in the upcoming units. Challenges we have, sometimes we have complex landscape, computational cost, and we can use multimodal optimization in function optimization, robotics, network design, machine learning, and other. So that's all about this video. Here we discussed what is optimization, that is the process of finding best solution. Aim is to either minimize or maximize the objective function. Then we have different key components: decision variable, objective function, constraints, feasible solution space, optimal solution, local and global minima. Then we have problems, optimization problem structure, then constrained, unconstrained, multimodal optimization problem, and we discussed one classical optimization problem, that is transportation problem. Aim is to minimize total transportation cost. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.